Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we have been seeing was this closed queuing network or closed junction network, otherwise called as Gordon Naval network. That's what we have seen so far. Now what we will see next is you can consider that as a special class or a specialized version of the closed queuing network. So what is that? So this is called as cyclic queues or cyclic queuing networks. This what we are seeing is a special case of closed queuing network, but this can also be put it into an open version actually. But this is more in the case of closed queuing network that it finds lots of applications. And in fact, it arose in a study of Taylor and Jackson in 1954 when they introduced this concept of this cyclic queue as a model for analyzing the flow of aircraft engine from operation to maintenance and again to operation, right? Operation, maintenance, operation, right? You can think of this again something similar to your machine repairment, similar, okay. So this is, they use this as a cyclic queue and then they try to analyze and then try to get insights about the system. Of course, since then there have been a lot of work which has been done on this. Okay. So this is, what is that then is a cyclic queue or cyclic queuing network is, it's basically a sort of a series queue in circle, okay, where the input of the last node feeds back into the first node. So if I want to put diagrammatically, so there is this node 1, okay, and which feeds into node 2 and so on. So there is this kth node, right. So this comes from here, right, the arrival comes from here. So this is the kth node, right. So you can call this as I think mu1, mu2, and assume that you have mu k. Then what happens, right? So this comes as an input to this. That's what it is. Okay. So you have a certain number of fixed number of customers who are circulating in this network in this manner, one after the other, right. That is what we are seeing it here. This, after this they go to queue node 2 and so on up to node k, and then so you can call this as node 1, node 2, node k. It is a very simple setup. So like series was a special case of the open network. So this is basically a series in queue. So you can in fact draw this diagram in a circle like this, right, so that the connection becomes very nice. Here we have to connect it from here to here, but if you draw in the circle like this, it will come naturally to that. So it is also called circulant network. Sometimes this kind of things is also called in that fashion. Okay. So what is the setup? That if you consider a closed network with k nodes like this, then my Rij, which is the probability of moving from I to j at the end of service completion at node I, is 1 if j is equal to I plus 1 for I 1 to k minus 1, and when I is k, j is 1 right, that is this link, it is 1, right. All other Rij's are 0. Then we have a cyclic queue. So, if I take this particular Rij's, then what you are going to get in a closed queuing network is a cyclic network. So, since this is a special case of closed queuing network, the results of the closed queuing network applies here, as it is, right, one can apply, but since this is a specialized one, so you can always get something more out of that than the general. So, for the time being you can assume that there is a single server at each node. Then we know the joint system size distribution would be a product form of this nature, and the which is basically some constant times rho 1 to the power n1, rho 2 to the power n2 and so on, rho k to the power nk, and the traffic equation, right, the traffic equations here, if you substitute the particular Rij's that we have here, would be reduced to this for I is equal to 2 to k, and for I is equal to 1, which is mu 1 rho 1 is equal to mu k rho k, is what then you will get here, right. Many a time, because we know that this is mu I, rho I is the relative utilization and mu I rho I is relative throughput, which is relative lambda i's, right. So, you would find in many situations that people write it mu I, rho I as a single quantity, like we have did for the MBA algorithm kind of thing, right. So, that's mu I rho I together, because whether you are determining rho I or mu I rho I together, it is one and the same, right. So, that is why one writes it in that form also traffic equation, but we will keep it in this form. So, this mu I rho I, if we just put, because there is only one value which is 1 out of all these, so that means that the corresponding entry only, like you will have this. So, this becomes this, that means my rho I is equal to mu I minus 1 by mu I times rho I minus 1, or mu k by mu 1 in case of I is equal to 1, right. So, that is what you will get as this rho I. Now, once I know the rho I's, then I can put it here, right. So, this is actually like this we are writing in expanded form here, that means rho 2 is mu 1 by mu 2 times rho 1, and rho 3 is mu 2 by mu 3 times rho 2 actually. So, this is product, okay. So, from the first equation, this is the second equation, that is what you will get here, and so on you will get, then you will write this in terms of you plug it here mu 1 by, for rho 2 you plug it here again, you will get mu 1 by mu 3 times rho 1. So, rho 3 is mu 1 by mu 3 times rho 1 is what then you will get, because rho 2 is this, when you substitute here mu 2 will get cancelled and rho 1 will get, then mu 1 by this is what you will get here. So, you get all the way up to, then rho k minus 1 is mu 1 by mu k minus 1 times rho 1, and rho k is this. Now, if you substitute this here in this equation, right. So, to solve this, what we have to do is that we know that the system of equations is linearly dependent, and that is what you are coming out here. You see, everything can be expressed in terms of 1, but they cannot be independently determined, right. So, you have to set rho 1 equal to 1, then rho 2 is equal to mu 1 by mu 2, rho 3 is mu 1 by mu 3, and so on you will get, right. So, that is what you will get. Now, once you plug those quantities here for rho 1, rho 2, then you know that this mu 1, because everywhere this is mu 1 here, right. So, mu 1 to the power n minus n 1 and divided by this quantity with appropriate normalization constant g of n would be there here, because we are assuming n customer in the system. Now, this g of n can be computed as earlier, right, either through naive procedure or through convolution algorithm or Buzan, that is what is Buzan's algorithm is, right. So, somehow you can compute this, then you determine this joint distribution. So, its simpler form is what then you are looking at here, right. So, it is mu 1 and mu 2 to mu k is what are the parameters of the model that appears in this fashion for the, and you know that n1 plus n2 plus nk is is what then you are going to get here, okay, because if you sum n2 plus n2 nk, this is what you are going to get from here, okay. So, this exact same expression, because you know in multi-server case what will be the change that we will be affecting here. So, multi-server case can also be treated similarly without much difficulty when you are looking at this cyclic queue. Okay. As we already pointed out, the machine repairment problem is really a 2-node cyclic queue, one node for operation, the other node for, as usual, for the repair facilities, and then the items will move from one to the other in a cyclic fashion, right. So, that is basically a 2-node cyclic queue is what. It is a very simple network, but many a time the analysis would help us a lot, depending upon the situation that you would have, because there are many more specialized results which can be obtained for the cyclic queuing network. Okay, that is possible. Now, as an example, consider a cyclic queue with 2 nodes and k circulating jobs. This k we are keeping it, we are picking it to be k for some reason. You will just realize it later. Okay. So, k circulating jobs are there, 2 nodes are there. Like simple example, the first node is an exponential server with rate lambda, and the second node is an exponential server with rate mu. Now, remember, this can be viewed as a special case of a 2-node closed queuing network example that we have considered earlier, right. So, there is 2 node, and after each node there could be a feedback with certain probability, and it could go to the other node with certain probability. That is what we had it there. So, now if you remove that feedback 1, okay, then what you are going to get is exactly this problem or this example that we are looking at it. So, there in that model, if you are keeping in mind, if you substitute these parameters, right, there we consider m jobs. So, now we are putting it as k jobs. This p and q for the self feedback, immediate feedback, which we make it 0, then it will go to only the subsequent node. So, and with rates as lambda and mu in the 2 nodes, if you substitute, then you are going to get this back. Nevertheless, even without going there, so you can consider this as it is, and you can write the traffic equation. Now, you can see really the traffic equations becomes, it just the 2 quantities, and it is the same equation is what you are getting it. So, there are 2 unknowns, 1 equation, right. That is what would happen in general case as well. Okay. So, we can set one of them. So, rho 1 we pick it to 1. So, rho 2 becomes then lambda by mu if you substitute from here. So, this rho 1 rho 2 there in the general solution, then this is what you will get 1 by g of k times O2 to the power m, much like the earlier this example that we have considered. Then 1 over g of k, this rho 2 is this simply this, you can write, right. So, this is the solution, where the gk is essentially this quantity which is sum over all this, which is turning out to be this. Now, if you substitute gk here, then I will get a complete expression, but remember here we have assumed this is a generic lambda by mu, but now we can generalize or be little bit more specific for 2 cases. One is when lambda not equal to mu, and when lambda equal to mu, this is really 1, right. This is also 1, and hence this is also 1, and hence like you have to appropriate this is 1. So, you will simply get as the required quantity only, like k plus 1, right. That is what you are going to get. But if you write for both these cases explicitly, like lambda equal to mu, lambda not equal to mu, then the complete steady state solution you can see is basically this one, 1 minus rho 2 O2 to the power m by 1 minus rho to the power k plus 1 for rho not equal to 1, and for rho equal to 1 it is the discrete uniform is what you are getting here, and for m is equal to 0 to k. Now, look at this distribution, look at this quantity, right. This we have seen already, and that is corresponding to an MM1K system, right. If you have an MM1K system with the parameter lambda and mu, right, if you obtain the steady state number in the system in that MM1K system, then you saw that you obtained exactly this expression where rho 2 is lambda by mu. So, here, so this one also you are obtaining it to be exactly the same. So, that means what? There is an equivalence, right. This kind of things we have seen already. Say for example, in the case of Erlang and in the connected with the bulk, right, Erlangian models to the bulk queues, like we have made the equivalents. Similarly, for the cyclic ones, right, the finite space model, one can make equivalent, so that the properties can be studied nicely. And again, I would say that you can, if you are interested, you can look in the literature that how these kind of equivalents have been utilized to study a queuing network, or the other way around, whichever way. So because these are in some way equivalent system, right. So this 2 node cyclic queue, as we described here, it may be considered as an equivalent to MM1K system, and this might be of some help, as we said, when we try to analyze the model in some details in this case. Okay. So that is the example that we have. Again, we said that this is we consider as a closed queuing network. So you can also think about a open network scenario also, but more application oriented stuff happens only in the closed network context. So that is why we restrict here. Again, one need not study this separately, because this you can study as a special as a part of closed queuing network. Similarly, the open one you can study as part of an open Jackson network, no problem. As we always say, it may be convenient, it may be useful that you study these special systems in more detail, to which to that end, like that might be of some help. Okay. So that is what is about cyclic queues that we are seeing it. Okay. Now we will try to end this discussion on queuing network on what was further happening and what are the directions in which this has gone ahead. Because what we started, when we started, we said that we are going to look at within the Markovian framework only, Markovian network only. We are still within that. Even within that, there are a lot of extension, and there are beyond that also there are. Now if you look at Jackson network itself, we will see a certain extensions of Jackson network. We are not going in detail, but we will just highlight what are the extension and so on. So as we said, there have been many directions in which the Jackson networks have been generalized, like to include state dependent arrivals, state dependent service, and the travel time between nodes, right. It may not be the case that the customer who leaves the previous node, suppose the following node is empty in a way. So then his service starts the moment he leaves the previous node. Okay. So in that case, what we are looking at, suppose if he is going and waiting in the queue, then it does not matter, but provided if that server is free, then we are taking it in our model things like you can understand that as if his service, the second service for the second at the subsequent node, the service starts immediately at the moment his service is completed in the previous one. Okay. But that means that we are assuming that there is no travel times between nodes, but in reality there are some travel times. Now how one can do? One way is you think the travel time itself is corresponding to some kind of node. Okay. So the travel time between one, that you see is a node with multi server, ample server, infinite server, so that everyone keeps moving without any hindrance. But if there is a hindrance, then again you have to models appropriately. But without, if there is any difficulty, if they are moving, then you can think that is corresponding to an infinite server model, and then one can put certain time duration, that will be the travel time for that node. Okay. But otherwise one can explicitly also incorporate the travel times. These are all certain extensions that has happened with respect to Jackson. Jackson himself did say, for example, this state dependent exogenous arrivals and so on few years later, when after he gave the first ones. Okay. But out of all those extensions, the most significant and the useful form of extension of Jackson network was to the case of multi-class network, or a Jackson network with multiple classes of customers, and in addition to that, along with certain queuing disciplines, right, which is what is considered by Basket, Chandy, Muntz and Palacios in 1975, and with their first letter. So these networks are called as BCMP network. This is the standard network because this has lots of features and it can quite very well incorporate the things that you want to do. So, in use, if you see, if in use today, BCMP network would be the most useful network that you could see. So, what are this? So, this BCMP network considers different service disciplines as well as different classes of customers. Say there are Q classes of customers. So, you have as usual K nodes, Q class of customers. Customers circulate in the network and may change class as they move from one node to the another. Okay, this is a main feature, that they are not remain in the same class as they move through the network. They keep changing their classes, right. Maybe this fellow, I mean, you can look at in some manufacturing or production. So, some processes might have come, some process might have come. After that, when you put together, this brings out to some other classes it might go, depending upon what had happened, right. So, the classes changing is also a relevant feature in many situations. Okay. So, this BCMP considers such a scenario that they may change class as they move from one node to the other. So, for example, a customer of class R completing service at node I next goes to node J, right, as a class S customer is denoted by PIR comma JS, and hence the routing matrix would be of this for I and J of this, and 1 and R and S are between the classes. So, the service rate of a customer of class R at node I is in general assumed to be mu I R. This is some basic fundamental setup that you have here. In addition, the product form solution, where is the usefulness when we said we are still within the realm of your product form networks. So, that is what is the main idea. So, this BCMP network gives product form solution for this whatever the basic setup or basic assumption that we have given for the following cases of queue disciplines. One is the processor sharing queue, which processor sharing queue means that the available service capacity is distributed equally among the customers who are waiting in the system at any point of time. That is a processor sharing, like our internet, whatever is happening, right. And ample service, which means any number of servers, inference server case, and last come first serve with preemptive resume servicing. Okay. Now, here in this setup, when BCMP gave this result of the product form solution, they did give for this in that generality as exogenous Poisson input with state dependent and service distribution can be phase type. It is not just need not be exponential. That is why we just talked about the rate here, we did not talk about the distribution of for which this is the rate, right. It could be even phase type distribution. And also they also gave one more class of Q disciplines for which this product form solution holds, that is for a C server FCFS node, but now the service times of all classes must be IID exponential, which means what? As far as node is concerned, all customer types look alike. There is no distinction between, right. So, it is as if only in that case they obtained the product form solution. Of course, there were generalizations again, as happens in any area from that point onwards along these lines. This is one of the most useful, and of course, one can easily write down with these assumptions like the traffic equations, obtain the solution and write down the product form and the normalization constant, you can obtain it much like the other queuing networks that we have considered. Okay. So, is not much difficulty there essentially, right, once we specify the assumption. But anyway, we are not going into that. So, I am just highlighting that there is some such thing called BCMP network, which is what is the most useful form of queuing network as far as applications are concerned. That is what you have to take it. Okay. Now, Kelly considers some other generalizations of Jackson networks, and that included extensions to some of the most general queuing disciplines. In fact, the BCMP whatever the consider, most of them also would fall within this generalization. Okay. he obtained product form solution with Erlang service distributions in the general setting itself, and also conjectured for more general distribution also that must be true, because only the mean service time and was appearing in the product form. That was the reason, like, but then it was proved later anyway. So, that is true, that for general case also that is true. So, this BCMP extension network and Kelly's extensions, in fact Kelly's book reversibility and network, it's available freely online, and where he had given lots of work on whatever he has done along with up to that point of time. It's a very good resource if you are looking at something on network and more details, okay, right. So, that's these are theoretical developments, okay. At the same time as these theoretical developments happening, the theory developed, when the product form solution, always you look for product form solution because that makes your life easier. If you have to keep it as it is in the full generality, like what happens in the case of a queuing network with blocking, then the complexity is, it's exponentially very high, right. So, it's very difficult to handle, but even so you want to keep it still in product form, even then you have a lot of issues with computationally when you want to compute. But when you do not have product form, then it's very difficult to do that, of course, okay. So, that is why you keep looking for under what is the generalization that I can make, so that I am well within the product form solution format, okay. While this was happening, there were attention were also towards efficient procedures or algorithms for obtaining the computational results. Again, in each case you have to look at the normalization constant, for example, whether it is open or closed network, whichever form you are looking at it, you still have to compute that, because the product form, it is even in open case, we did not assume that it is basically factored into the product of marginals. It's just that it's product form. So, still you will have a normalization constant which you need to compute. Obviously, in closed queuing network, that's a inevitable thing, but in open also, like within that form only, like we are calling it as product form network. So, within that, then again you will have a normalization constant. Now, how you will compute in efficient way, all that aspect also have to be looked at. Otherwise, in the theoretically you are developing, but the applicability will be limited if you are not having a procedure for that. So, that side by side one has to look at that aspect as well, and that aspects are going on till today. You can say that the various extensions keep coming, and then depending upon the necessity to model many real life phenomena as they evolve, like the more complex situations that comes, the more complex model will become, and then you try to analyze that, then you try to see how we can implement it, then computational aspects you always look at. So, this is a never ending process. So, it is always on, like in any other field. There is nothing peculiar about queuing network or queues alone that such kind of scenarios are happening. So, it is across the board for any research to develop, okay. So, that is the we will end here. Of course, one can also talk about non-Jackson network as an extension, and something called as loss network. See, here we have assumed that all MM1 type or MMC type in each node. Suppose if you have, instead of this model, if you are keeping loss model, say for example, the Erlang's loss model, suppose if you are keeping it in the as part of nodes, then such a network is called loss networks. Again, it has applications in computer and communication field, such networks. So, one can talk about like this with different aspects, different angles beyond even Jackson network, right. But that is for you to explore further, okay. So, we will stop here our discussion on this queuing network. We have just restricted ourselves to Markovian framework, consider open and closed queuing network, basically open Jackson and closed Jackson network, and how one can handle that situation. That is it, okay. Thank you, bye.